let us begin. There's no quiz today because I want to have a good shot at finishing chapter 9. It's actually a lot of stuff. But we'll try to get through it. Yes? The next test will probably be the Thursday before finals.
Thursday before the final.
I don't know what's right. So finals is the week of the 20th, right?
Yeah.
So our final will probably be on the 20th, so the last test is probably the 16th. Final will be July 20th. Here in Boston. Same place, same by China. Okay, so about the test, just a few things that stood out. There weren't a lot of quick problems, so. First of all, if you got below 60, you should see me, probably on Wednesday. You sort of email me and set up an appointment. But other than that, some of the common mistakes. Begging the question, I warned you guys about this. I saw that a lot. People assuming what they needed to prove. That actually happened quite often, too often. You have to be careful about that because I'm like I said, it can sneak up on you and you don't even realize you're doing it. You have to be really careful. What are your assumptions? Bad assumptions in general were prevalent. So, bad, pointless, or untrue. Right, so there were times where, for example, I was asking about a set, and someone just assumed the set was closed, right? You can't just make assumptions like that. Like if I don't tell you the set is closed, don't assume the set is closed. Don't assume it's open. Don't assume it's neither, right? Like if I just say, okay, we have a set and prove this. You have to be careful about the kinds of assumptions you're making on that set, right? If you don't know that this is the case, you can't just assume things like that. So I saw people just assuming random things. I also saw people a lot of the times assuming what they want to prove, which of course is going to work out. You're assuming what you want to prove. Another thing, lack of fact checking. If you're going to state something and you're not going to prove it because you think it's simple, you have to at least make sure it's true. There was the one where we were trying to prove that there were an infinite number of irrationals between any two real numbers, and several people, more than a handful I think, they had this, okay, pretend there's an R between these two, then they said this. You can find another one in between it by just dividing by 2. Is that true? No. Like, why could you even make that assumption? Why would you assume that this is true? When it's not. Like, I gave people some examples, right? 2 is less than 3, but 2 is actually not less than 0 or 2. Right? If I divide this guy by 2, I can't guarantee that he is, right? I can't guarantee that dividing this by 2 keeps it above the A, right? It's possible for me to divide by 2 and I move over here, right? So I saw, like, it was a handful of people, maybe even more, did that whole dividing by 2 thing. you can't guarantee that it's going to be between the A and the R, this division by 2. So when you say things like that, you're like, oh yeah, it seems like you don't have to prove it. Be careful what you're saying. Some people just said these things that are just, what? Like if you tried with any random numbers, almost the chances of you proving them wrong is so great. What else was there? Oh, I saw assumptions like, well, if A is less than R1 less than R2 less than B, then I think someone added both of them. Right? And that's clearly not true, right? It's possible for the sum to even be outside of here. One thing that would be true is, that would be true, right? Because that's the average, it's going to be in between them. Someone actually used the average. In my proof, I didn't use the average, but they got full credit. They're kind of sloppy, they didn't set up everything correctly, but for the most part, they got it correct. And I was like, yeah, okay, that's a nice solution, right? So they just showed, you know, once you can find 2, then you can find a new one in between any 2 by just averaging the 2 rationals, which is fine. Some people used A in their formula. They said something like A plus R over 2. The problem with that is A is a real number. You're not sure it's rational, so you can't really make that claim either, right? So that wouldn't work, right? But as long as you use 2 rational numbers, the average would work. But I've seen people just add the 2, which is, it's not true. Right? Be careful of what you're saying, right? Check your facts, right? Whenever you're doing something. I know it might seem to you that it's simple, oh, we're just dealing with these numbers and inequalities, and you can deal with them all your life, but it's still easy to make a mistake. Be very careful, right? So be careful of your assumptions. Don't assume something that's not given. You want anything that's not given, you want to prove the most general possible, right? You can prove by cases, right? So if I told you about a set, you can say, oh, what if it's closed? What if it's open? What if it's neither? And you can do a proof for each case, and that would be fine. But just assume it's closed, and then you prove it. Even if that's correct, you haven't proven the claim. You only proved the claim in one situation, so be careful with that. So those are the 3 main things that jump out at me. The 4th thing. People still don't know how to prove 2 sets are equal. You have to show this and that. You can, in the question that I asked in problem 5, I think, there was a way around proving both subsets are equal, right? Like I think 2 people got it, where they were like, okay, if you take the union of this side, you'll have to get the other side. And they gave me an argument for that, where they didn't really show the subsets. But I saw a lot of people only proving one of these. They proved, oh, this one was a subset of that one, I believe it was. You wanted to prove that A was equal to A minus B intersect A and B, oh, union. Now some people actually explained in words and they gave me an argument why if you take the union of this and that, right? They broke down the definitions and say, oh, this is A and you throw out all the elements of B. This has the guys in B and A, so then when you put them back in and blah, blah, blah. They explained that and that was okay. I would have given you most of the points, if not all of it, for such an argument. But a lot of people didn't prove both of them, right? They decided to prove one and then left it. What else did I notice? A lot of people attempted to prove both, but they did it the wrong way, right? You have to remember, to prove that A is a subset of B, you have to assume X is in A implies that X is in B, right? And so if you want to prove this, your assumption should be this, which sort of ties back into this. I saw people assuming some crazy things, assume blah. Sometimes they assume things that it actually doesn't make sense to say it. Like I've seen people write things like assume. They like assume this. You actually haven't said anything. That's a meaningless sentence. Okay, assume that. What are you assuming if you assume that? Nothing, right? If you don't have this, it's a meaningless sentence, right? It doesn't. You just said gibberish by not doing the x as an element of, right? You have to assume that there's something in this, some element x in that, and you want to show that that element is in the other set, right? But if you just assume the set, you're going to do it. Assume A, right? Or assume the integers. What are you saying? Right? You can't really start by assuming a set. That doesn't make any sense. That doesn't really say anything at all, actually. So yeah, look out for these questions. Be careful of your assumptions. In particular, be careful of assuming what you want to prove. Be sure to check your facts, right? Your arithmetic. Make sure that you're not divided by 2 when it doesn't work. It doesn't work to divide by 2 in this case. Or other cases where it doesn't work. I also saw assumptions like, what did they say? It was something similar to this. I believe it was in the supreme question where they assumed something like A is less than or equal to B, and then they showed that A is less than or equal to C, and their conclusion was B equals C, which is not true. Clearly, right? Because 2 is less than 3, 2 is also less than 5, 3 is not the same as 5, right? Be careful with the facts that you're doing. Yeah, so just some things to think about. And like I said, if you got below 60, you probably should talk to me this week. Email me, set up an appointment. We can meet Wednesday or tomorrow. Tomorrow is also fine. But yeah, be careful. Sure, you've seen that in your class. Okay. So that's that. Let's continue with functions. So we have a lot of stuff to cover. For the most part, the ideas should be familiar. Like I'm going to talk about compositional functions and inverse functions and all that. And we've all seen it before, but we're sort of going to come at it from a different angle, from the angle of proofs now. So it's going to be different, but the familiarity of the subject should give you some comfort. So we defined what a function was. What is a function? How do we define it?
Relation between 2 sets such that for each point in the first set you have corresponds to 1 point in the second, or 1 number.
Right. So a function from A to B is just it's a relation of A cross let's write it down. I say f A to B is a function if f is a subset of A cross B such that right, so you have to use all the elements in the first set. For each A is related to exactly 1 B. Right, that's what gives you a function. All right, and we mentioned what a function is. We talked about notations. We talked about what the domain, codomain, range are. I gave you examples of functions and things that are not functions. We talked about what two functions were equal, yes. I told about other ways to write functions. We did the formula, mapping diagrams, graphs, right? I drew a graph. Did I tell you about the image? Did I define image last time? I don't think I think I stopped just before that. Okay, so let's pick up there. So suppose from A to B is a function. And suppose that C is a subset of A, then the image of C is what I want, is the set f of C, we're going denotation, and it's the set of all outputs such that X is in. Yes, such that X is in C. This is the definition. Alright, so basically here, I have the set A, I have the set B, and I look at a subset of the domain, call it C, and then I only look at the elements that those guys get mapped to over here. This I call f of C, and it's actually another set of elements, right? So this guy here is called the image of C. Okay, note. F of C is obviously going to be a subset of B, right? You can't ever have elements out here mapping outside of this because B is the codomain. You'll never get outside the codomain. You wouldn't have a function in the first place if you did. So maybe I should do a concrete example. Let's say A is the set 1, 2, 3. B is the set A, B, C. Let F let C be the set 1, 2, and F equals 1 goes to A, 2 goes to A, 3 goes to C. Then, what's F of C? Just A, right? The set of outputs. We don't put the coordinates in here. The image is not a relation on its own. It's just a set of outputs, right? We call it the image. So we just look at the subset. We only focus on where these two guys go. 1 and 2, they both map to A. And so that is the image, right? So that's just an example. What else? Did I define what an inverse was? Yeah. I did? An inverse function? No. Well, an inverse relation we know about, though. I'm actually going to come back to inverse functions later, after I talk about bijective functions. So suppose f from A to B is a function and D in this case is a subset of B, then the inverse image of is F inverse of D. And this is just going to be the set of all A in A such that F of A is an element of D. It's talking about inverse image. So what the picture looks like, this is A, this is B. So here is my D. It's pretty much the same picture, but we're considering it going backwards because we're talking about inverse functions. We're going to come back to this later. So the set of all things that come from whatever set maps elements here, we call that F inverse of D. So example. What is F inverse of D? It's on the element 2, right? So basically now, instead of looking at the inputs, we're looking at the outputs, right? Where are the outputs?
And 1.
B, 1, yes. So 1 and 2. I fit it. 1. Right, so I'm looking at the guys who mapped to B and D. Right, no one mapped to D, so that's fine. It's possible for the inverse image to be empty, especially if your function is not onto, which we'll talk about onto later. Right, but we're looking for the guys that map to either B or D. Well, 1 and 2 actually do, so they're both in the inverse image. Similarly, if I want the inverse image of one particular element, that's just the set A and A such that F of A gives us that element. So it's just a specific example here where your D has one element in it, then you just look at all the guys that map to that element. Let's do an example. Suppose F from A to B is a function C is a subset of A, D is a subset of A, E is a subset of B, F is a subset of B. Show that let's look at that. Are these sets? Yes, exactly. Functions are sets. Remember, that was the definition. It's just a set of ordered pairs, right? So yeah, if I want to prove this is equal to that, I'm actually proving one set is equal to another set. So I do have to show inclusion in both directions. Remember, functions are sets. Right? There are sets of ordered pairs. In this definition, of course, you can have ordered triples, but that's multi-variable stuff. We're not going to do with that. But yeah, these are sets. So we're going to prove them the same way that we prove for sets. Right? So we need to show that f of c union d is a subset of f of c union d, and f of c union f of d is a subset of f of c union d. That's the first thing I have to show. That's the second thing I have to show. Let's show the first thing. So what do we do?
Assume that x is an element of C union D.
What does that mean?
That means that x is an element of B, which corresponds to an element in either C or D.
It means x is an element of what?
Of B. That's corresponds to an element of C or D. Right? Because the definition of
Is that two b's? Yes. Okay, so you're saying then
that x is an element of B, which corresponds to some element which is like in C or D.
which corresponds
Which
to what?
corresponds to an element of C union D, if you want.
Say that nicer.
Okay. So that x is an element.
What do you mean corresponds to?
Which relates via the function f to an element of C union D.
Such that there exists y Is that what you want to say?
Yes.
Yeah, okay, where do we go from there?
So then y, because y is an element of C, union D, y is an element of C. Or
This means
D.
y is an element of C or y is an element of D. Okay.
That means that x is an element of f of C or f of D. And therefore x is an element of f of C union.
Alright, so remember what we're talking about when we say f of this guy, we're talking about the output. So we're looking in the codomain. So we wanted a picture here. Often when doing proofs about functions, mapping diagrams are very useful. So I recommend, they don't come as proofs, but they're useful in thinking of the idea. So let's say we have here a set A, over here we have B, and inside B we have a subset C and a subset D. Right? They may be joint or disjoint. And we want to prove that the outputs that we get from C or D is equal to so the idea is here. C is not here. This is f of C. This is f of D. and C and D are over here. Right? So C and D are subsets of A, right? And let's pretend that the elements of C map to F of C, the elements of D map to F of D. Right? So basically I want to say that the output of the union is just the union of the outputs. That's what we wanted to prove. Right? So then you're like, okay, so if we pick a set in here, in this set, then it must have come from either C or D, in which case then you can come up with the union. Right? Going the other way, how do you prove 2? Prove that one set is a subset of another set.
Wouldn't it just be the same steps for going back?
Well, you'd start out with assume X is in F of C union F of D. Then, how do you finish it?
X is another one of F of C, or X is another one of F of D. There is this Y.
So there exists Y.
Well, would you say inverse? There is this X. No, there exists a Y such that F. F inverse of X is Y.
F inverse of what?
X is Y.
There's some y in C or D, such that f of y is x. Or
Right. Be careful when saying the inverse. The inverse in general we haven't defined yet, and it's sort of tricky because it won't work in all cases. An inverse doesn't always exist.
where's that one?
So it would just be F of X.
So there's a
F of
so then such
Why
that.
is that one in D? Why is that one in C or D?
Coming in?
So why is that one in C or D?
Right, so if this or this is true, then it means that there's a y in C such that f of y equals x, or there exists y2 in D such that f of y2 equals x. What can you say then? Right? Then you can say if y1 is in C, then clearly y1 is an element of C union D. Right? And then that just gives you that X is an element of C union D. And then if you have y2 is in D, then this means y2 is clearly an element of D in C, which means that f is an x.
Do you need to state a second?
Well, there are really two cases. They could actually be different numbers. There's no telling that the guy is in both C and D at the same time, right? We don't even know if the intersection is empty. I mean, I drew it here where they overlap, but they didn't have to overlap, right? This is one of the problems with pictures. It doesn't give you the full picture. Okay, so x is C. It was also probably pretty easy here to use the contrapositive of what I said here. If I assume x was not in this, then I know that this would not exist. So you could even do part 2 by doing the contrapositive of this part. You can try to see if you feel that's easier. That would work also. Actually, let's write that down. Let's see. 'Cause I'm not sure if you guys are getting used to this yet. I'm not getting a lot of responses. Or 2 by contrapositive. How would you do that? So you would assume x is not in f of C and D. What could you say then? What can we say about this y here? There is no y in C or D such that f of y equals x. Right? The opposite here must be true. If x isn't here, it means you can find a y in that set such that that's the output. However, if it's not in there, it means there is no y such that that will be true. So what does that mean?
C or D.
Yeah. Not an element of C, and it's also not an element of D. Are we getting this? Is it tricky, or is it just Monday? What is it? Long 4th of July weekend, a lot of drinking. We still have our meeting. We really need to get a move on it. Lots of stuff to do. Let's do another claim. So one of the main things to keep in mind here is that functions are sets. So pretty much all that your arguments can boil down to an argument about sets. So if you really know how to deal with sets, functions should be okay. It's just getting used to the notation and the idea of mappings. How do you prove that? Well, we need to show that this guy is a subset of that. And that's the first thing we need to show. And 2, we need to show that this guy is a subset. Okay, let's do one.
Can I draw a picture first?
Sure, we can draw a picture for it. So here's our A, here's our B. Now I said that E and F were where? They were subs.
And B.
They're in B. So here's E, here's F. And by our definition, there is a F inverse. There's a pre-image of E, and there's a pre-image of D, of F here. Right? So I want to show that the union of these two is equal to the union of
Image of B.
right. The union of these is equal to the union of E union. If I look at this as one set and find its pre-image, I will get the same thing as if I looked at two of these sets separately, found the pre-images of each, and took the union. That's what I want to show. So,
So, let's assume X is an element of the image of the union of.
right, so I'm going to assume X is in here, which means it can be here, it can be here, it can be here, right? So your X can be in any one of these. If the intersection could be empty, but it doesn't have to be. So I'm going to pretend there's an X in here. I need to show that it has to be in the whole thing. So let's go. So assume X is an element of F inverse of E union F. Then
There's a Y.
Then there is Y in what set?
There's infinity.
Such that
That's equals.
is that what we want to say?
So it'd be over.
B is too big, right? We'll never be able to say anything for sure. I know there must be a Y in E in F such that that is true. Then what can we say? Then Y is an element of E, or Y is an element of F, which means
It's an element of E union F.
we already have that. We have the
Oh,
union
sorry.
here. I want to break these apart. I want to break this function apart. Which means X should be an element of F inverse of E, right? Because if your Y is in E, then it means your X is in the inverse of that. Or if your Y is in F, your X would be in the inverse of that. So you're just saying, depending on which one of these sets it comes from, I can have what I want. So what about 2? So if I assume X is an element of this, then it means that X is an element of this guy, or X is an element of that. So if X is an element of that, that means there exists a Y in E such that f of x equals y. But y in E implies that y is in E union F. So X is an element of pre-injective union. Similarly, if X is an element of the inverse of F, then there exists Y in F such that f of x equals y. But y in F implies y is in F union E, which implies proofs with functions are like proofs with sets on steroids. You have to be worrying about, be very careful where your elements are coming from and where they're going to. Right? So, any questions? Do you have a question? Any questions? Do you get the overall idea? Not the specifics. So basically we're jumping back and forth between the domain, and we're like, if something, this is happening in the domain, it must mean this sort of thing is happening in the range, and back and forth, and you have to sort of worry about where things are coming from and where they're going. But that's all under the umbrella of worrying about sets. You know, we have to prove that if something's an element of one thing, it's an element of the other thing. I guess after you practice some homework problems, you understand what questions you have. Let's look at another important concept. This is going to come back in chapter 10. A set of functions from A to B. I'll say I don't want the trivial case. For A not empty, B not empty. Right, so I want the set of all possible functions from A to B. Right, that's what we're going to talk about now. And this set has this notation. You put the set B and you raise it to A. Right? This is the set of all F such that F from A to B is a function. Right? So B to A is just a set of functions. Why do we write it as B to A? Well, we're going to see right. I'm going to tell you right now. Well, I gave you an example and then I told you. Suppose A equals the set 1, 2, and B equals the set A, B, C. Find b to the a. Let's look at all possible functions from this set to that set. Let's start with the first function. Tell me a function from a to b.
1A, 2B.
1 goes to a, 2 goes to b. But this is gonna, oh, they're gonna be a lot here. There probably should be a 3 here, a 2 there. Let's make it a little easier on ourselves. 2, 3. You'll see why it's easier in a bit. So one function here would be 1 goes to right? You can have a constant function, right? The second one would look similar, but you can have 2. You can have everyone going to b. 1 goes to b, 2 goes to b, 3 goes to b. Okay, what's another possible arrangement?
1A, 2B, 3A.
Maybe you guys should come up with a system.
So you have 3 choices.
You're going to want to, yeah, you're going to want to come up with a pattern so you can catch all of them, right? So usually what I like to do is, after I come up with the first one, I leave the first one the same and exhaust all possibilities for the other 2, right? And then I move on to the second one and then exhaust the possibilities of that one. So if I have 1 goes to A, I'm going to leave 1 goes to A and then come up with the other arrangements of this one. Well, they both go to A, so what if one of them goes to A? I can let 2 go to B, but 3 remains at A. Or I can let 2 go to A, 3 remains at B. Or I can let both of them go to B. Right? So I leave 1A, and now I'm just worrying about what 2 and 3 are doing, right? So they can both go to A, one can go to B, the other goes to A, or the other one goes to B, this one goes to A, or they both go to B, right? And now I can switch up on the first guy, right? These are all possibilities where 1 goes to A. Now look at the possibilities where 1 goes to B. Right? So then I can have both of these guys going to A. Again, I can have 1 going to A, the other going to B. I can have 1 going to B, the other going to A. Or I can have both going to B. Right, so you just choose who you want to send 1 to, right? And leave him there while you mess around with the other guys. And then you go to the next possibility for 1. And if there was we have to do, right? And then you go to the next possibility for 1, which is B. There are only 2 possibilities here. Right? So we have 8 possible functions. Right? Do you think you can give me a formula to get the number of functions? if I look at the size of this set, right, so at the end of the day, what I wanted to show was that b to the a is just the set of these 8 functions, right? So in this case, b to the a has 8 elements in it, and each of these elements are functions. And I also would like you to note in this case that the size of b to the a is actually b raised to the a, which in this case was 2 raised to the 3 equals 8.
Almost like they gave it that notation for a reason.
This holds in general. So, if A and B are finite sets, meaning they have a finite number of elements. And the size of A equals n, and the size of B equals n, or n. Then the number of functions from A to B is just this. Assuming they're non-empty. And you can do sort of an elementary combinatorial argument for this, right? You can say for each A and A, it has this many choices for what to pick, right? And then you just use the multiplication rule, and you can add them all up. So that function, that concept is going to be important when we're going to prove things about the cardinality of the real numbers and the natural numbers. We're going to use this idea. What else did I want to say here? There's a common practice. B is equal to something like 0, 1. And B to the A is written as 2 to the A. Just think of B having 2 elements and you put the number 2 there. It's a common thing. We're going to again see that in chapter 10. So I just don't want you to be surprised by it. Let's get to something more familiar, but again, we're going to do it in concrete terms using logical connectives. One-to-one and onto functions. Okay, let's talk about one-to-one. A function f from A to B is called one-to-one, or another word you'll see, injective, if. How do we know a function is one-to-one?
Element B that is contained F inverse.
You don't have to do it in terms of inverses. So what's the picture? This is A, this is B. Let's say these are our elements here. Describe what one-to-one would look like.
Just a straight line from one to
Okay.
another.
Is that one-to-one? Why not? Because you have 2 going to 1, right? This is a many to 1, right? 1 to 1 just means if you have distinct inputs, you'll have distinct outputs, right? That's basically what 1 to 1 means, right? So it means that once somebody is assigned, no one else can be assigned to that one, right? That's called 1 to 1, right? So how do you actually express that in terms of, say, logical connectors? That's how you want to say it, right? If the only way for the outputs to be the same, if the outputs are the same, it means they came from the same input, right? You can also think of it in the converse, right? If x1 is not equal to x2, then the outputs won't be equal. It's the same, sort of the same thing, right? But in terms of things being not equal is sort of weird to use in a proof, so it's better to use the converse and state it in terms of equalities, right? So once your outputs are the same, it means your inputs have to be the same. Because if your inputs were not the same, it wouldn't be 1 to 1, right? You would have like a many to 1 relationship, right? So the definition, by the way, actually tells you how to prove something is 1 to 1. So you see that statement here? This is what you need to show. So if at any point in the future I said, prove that this function is 1 to 1, you somehow have to prove this implication, right? Or give an argument for it. Examples. So an example of a one-to-one function would be something like f from R to R defined by f of x equals x cubed. Since if f of x equals f of y, this means that x cubed would be equal to y cubed. This means x must be equal to y, right? By taking the cube root of both sides. Also give you some non-examples. Stuck in calculus so much, not used to writing where it's coming from and where it's going to. We always assume it's R to R, but we can actually vary this. So if f goes from R to R defined by f of x equals x squared is not 1 to 1. So there are a couple ways you can show this. Note f of 1 is equal to f of minus 1, but of course 1 is not equal to minus 1. So that kills the implication, right? I have this is true, but that's false. That means the implication false, right? Because these are both equal to 1. Another way you can show it is that if you assume f of x equals f of y, then that gives you that x squared equals y squared, in which case you would end up with x equals plus or minus y, right? Which is going to be a contradiction, because a negative would be possible. And we don't want negatives, we want them to be exactly the same. In fact, if I wasn't sure and I tried to prove that was 1-to-1, getting to this point is what would hint to me, oh, maybe it's not 1-to-1. Okay, what's my counterexample? Well, it seems like plus or minus. Maybe if I choose a plus or minus element, it'll work. So that's another one. Let's talk about surjective functions. You've seen one-to-one functions before, right? Okay, so this is not like terribly new. Maybe you've never had to think of them in this way, but I think you should have seen one-to-one functions before. You should have also seen onto functions before. So let's say a function f from A to B is called surjective or onto if
Inverse image of B equals A.
can't do inverses yet. Come again? For every element of B, there exists an element of A such that f of A equals B, i.e. the range of f equals B, right? The range is the codomain, right? Onto just means every element in the set here is assigned to someone. So A, this is B, and you have a function f, and it gets everybody. Everyone is assigned. Right? So in this case, you say f maps. I probably should have mentioned that before. I should have mentioned a similar language standard. We say in this case, f maps A onto B. Right? So it takes this and boom, slaps it right on top. Everyone gets a partner. Right? If f is 1-to-1, you say it goes into B, but probably doesn't catch everybody. If f from A to B is 1-to-1, we say f maps A into B. That's sort of where into and onto comes from. So let's look at some examples. Of onto functions. For example, f from R to R. F of x equals x cubed is onto. We're gonna fix this in a bit. How do you know that this is onto? So notice that if you assume y is in R, meaning this one, the codomain, then take x equals the cube root of y. Right? The cube root of a real number is always a real number. Right? Y could be 0, positive, or negative. You can take its cube root. And if I take f of x, which is just f of the cube root of y, I would get the cube root of y cubed, which is equal to y. Right? So for any guy I pick in my codomain, I can find a real number such that when I plug it into my function, I get that number. Right? That's what onto means. X squared is not onto because, for example, if I say minus 1 is in R, but there is no x in R such that f of x equals x squared equals minus 1. Right? That's impossible. Right? So I can pick a number here where there is no one in here that gives me that number. Right? So then it's not onto. There are guys in here that gets missed. They do not get assigned. Right? How do you tweak this to make it onto?
R, non-negative.
Right, change this guy. If I make this, now that's onto, right? How would I know that's onto? I just have to prove no matter who I pick, I can find a guy. So I know this is onto because if I say let y be in the non-negative reals, then who would map to that y?
Square root of y.
Right. X equals the square root of y is in the non. It's actually a real number. I can just look at it like that. And f of x equals x squared, which is equal to the square root of y squared, which is equal to, technically it's the absolute value of y, but because y is non-negative, this is just y. No, that's actually just y. If the square was under the radical, it would be. So I can just pick someone and it will work, right? And it works out because this guy is only positive. I don't have to worry about squaring things and getting negative numbers. Right? Only non-negatives work. Right? So that's an idea. On to another example. No, just fun fact, f is not 1-to-1, right? I want to emphasize that you can have things that are onto but not 1-to-1, and notice that this guy, you can have 1-to-1 but not onto, that's also possible. So if I look at f from R to plus. If I look back at this function, know that this is onto but not 1-to-1. Since, for example, both f of minus 1 and 1 give me the same guy. So you can be onto but not one-to-one. You can be one-to-one but not onto. They don't have to be both, and you can actually have things that are neither, right? It's not hard to have things that are neither. For example, this one is neither. Right, so you can have any variety of combinations of these two properties. I just want to emphasize that. F from R to R defined by x squared is neither one-to-one nor onto. So we're not going to finish, but I want to at least get some of the definitions out of it before we start practicing some problems. Next thing I want to talk about is the bijective function. They're also called one-to-one correspondences. Function f from A to B is called what's a bijective function? Huh? If f is one-to-one and onto, right? Has to be both. Can you give me an example, a quick one? X cubed, right? I already gave an example here. So f from R to R, defined by x cubed, is one-to-one. And it's onto at the same time. It's a bijective function. Here's a theorem. We're not going to prove it. The argument isn't that complicated, though. Suppose f from A to B is bijective, and the size of A is equal to the size of B, equals to n, which is finite. Then the number of functions from A to B is going to be n. That's not one-to-one and onto. Yeah, it's going to be n factorial. Proofs in the book, I'm not going to do it. There's another theorem that might come in handy. All right, so f from A to B is a function.
So when you're saying that the first one, you're saying the number of possible bijective functions between
Yes.
A and B.
Right, f is bijective. That's a key word.
So we're not really looking at the same B to A that we were looking at before, or B from A that we were looking at before. We're looking at a subset of B. Because
Yes. Yeah, you're right. I want to say specifically then the number, it will be a subset of B to A, the number of bijective functions. So I'm looking at a subset of b to the power a. Okay, now the theorem is f from a to b is a function, and if you're a, you know it's equal to b, then f is 1 to 1 if and only if f is 1 to 1.
If
A here now, R finite.
It works in the infinite case as well. Although proving this is sort of going to be weird. It actually works in general, but in chapter 10 we'll understand more about that. It works for infinite sets as well, but that's for another time. Also want to talk about the identity functions. Let A non to be a set. The identity function A is the function I, a subscript that goes from A to A, defined by whatever you put in, that's what you get out. Tells you the identity of your input. One more definition. Or after this, I have a few examples, but we're not going to get to any of them. So next time we'll kick the class off with some examples. Let's talk about well-defined. Talk more about equivalence relations. If equivalent representative of equivalence classes. So it's a well-defined function if it's actually a function, which means each input gives you exactly one output. Then you have to worry about the case where, what if you have equivalent inputs? Do you get the same output, which you need for a function? let me give you a non-example, it's probably more instructive. Define a function that goes from the rationals to the integers by f of a over b. The output is a. Right? This is not well defined, right? So I am making an assignment to a rational, but it's not actually a function. Why not? Give me an instance where this is not a function.
2 over 2 is the same thing as 1 over 1.
Right. So if I look at, note that 1 over 1 is pretty much the same as 2 over 2. As far as the rationals are concerned, these two are same equivalence class. They're equivalent. They're the same number actually, right? However, if I take f of 1 over 1, the answer is 1, while f of 2 over 2, the answer is 2. So I really have the same number going to two different things, right? So this is something you have to watch out for, especially in chapter 10. We're going to be creating our own functions. You have to make sure that the function you create actually makes sense. You have to make sure that it won't depend on how you write your input. Once the input is the same, the output should be the same. Which sort of gives us the short way to write down what this means. i.e., f is well defined if x equals y implies f of x equals f of y. Right? It's pretty much the converse of being one-to-one. You get well defined, right? If you have two things that are the same, their output should be the same thing, right? So just like here, if I have two guys, it doesn't matter how I represent my input, who I choose from his equivalence class, I should get the same answer, right? Because I have the same guy going to something else. Right? So that's a very important thing, especially when you're creating functions, which to prove a lot of things, you have to create functions from scratch. You have to be careful how you're creating them. Next time we'll start off with some examples to do with all of this.